You can see my screen, I think.
Yes, Doctor.
I'll just go through the problem that we did last time, because there was a small, not a mistake, but it is a mistake, but not in what we are doing, but in the numbers that were there in the slides. So I changed that. So just to remind you of what we did, especially for those who were not with us, but I think most of you were there. So we are saying that, let's say that I know where I want to be. I want to have my pool at S naught at this point. And I know zeta. I mean, I don't know exactly what is S naught, but I know zeta. So from knowing zeta, I can know this angle theta. This angle, I can calculate it, because theta equals cosine inverse zeta. But I don't know this distance x from here to here. I don't know what is this distance. I can know it by zooming into this from the figure, so I can know exactly what is S naught if I can draw this line. But let's say I want to do it by calculation. So if zeta is known as 0.5, I will substitute here with 0.5, and I'll substitute here with 0.5. I will get this equation. Now, how to make sure that this point is on the root locus? We need to satisfy two conditions. The first condition will make sure that this point is on the root locus by looking at the angle. So the angle have to add up to 180. And then I can get K, the gain. So let's start with the angle. So we want to know, to make sure that theta 1 plus theta 2 plus theta 3, this theta 1, and this is theta 2 here, and this is theta 3. So I want to make sure that those are, when they add up to 180. So theta 1, as we did last time, it is 180 minus 5. Okay. Theta 2 is tan inverse this length over this length. So it is PTY, because this length here is PTY from here to here. This one is PTY from here to here. This is PTY, which we have it. If we go back, this is PTY, and this is what you call X. So this is PTX, and this is PTY. We have them, and we can calculate them from the angle phi. So it is R cosine, or we have it here as R cosine. This one is R is here is X. So X cosine or X sine, which is this one. So we can calculate PTX and PTY. So again, let's go back here. So theta 2 will be this distance, which is PTY 0.866x plus 4, because this distance from here to here is 4, divided by this distance, which is 4 minus PTX. So this we did it correctly last time. And then theta 3 is tan inverse this distance over this distance. So it is 4 minus, because this one is 4, and this one is PTY again. So 4 minus PTY over 4 minus PTX. But this angle here is negative. It is in this direction. This angle here is negative. According to the diagram that I have, if I chose my S naught in the diagram to be here, then I'll put it as positive, because then it will be PTY minus 4 instead of 4 minus PTY. So since it's negative, I'll put here minus tan inverse of this. Okay, so minus tan inverse, according to my diagram now, it is negative, because 4 is larger than PTY, larger than this distance. So therefore, the angle is in this direction. Okay, so it's minus. This is the mistake that we made last time. That's one of the mistakes. So if I put this down, I will get the right answers, which is this one. The angles will be minus 132 if it is 1, if x is 1. It's minus 145 if it is 2, if x is 2, minus 159.9 if it is 3, and minus 180 if r is 4. So it means my r, my x, is 4. This distance from here to here is 4. From here to here, this distance is 4. So the mistake last time was not in what we are doing, in most of the what we did, but it was, the mistake was in this table. The previous table was wrong. So I think you got it. Is it okay? فالاشكاليه ما كانت في اللي كنا نسويه في اللاب، الاشكاليه كانت في التيبل اللي انا وضعته. يظهر اني كنت وش يسمى احل بدون ما كنت حاط هذا البراكت، فكنت اقسم بي تي واي على 4 ماينس بي تي اكس، وبعدين اطرحها من 4 الى this call or this what you call was not there in what I did when I presented that table, the wrong table. So now this table is correct. So this is the right table. And then you calculate K. K is 1 over D of S. So you calculate this length A, and this length B, and this length C, and you get the what you call the so this A is S naught minus 0, S naught minus S1, which is 0. B, this is B. It is S naught minus this. So S naught minus this. And the same for C, and then you just calculate all of this. So I did it using C lab, and I got it as 64, sorry, 64. I think I need to admit someone. Someone just arrived. Asif. Okay, so let's go back. So I think now we clarified that. We did that in the class, but there was a mistake. So I just corrected it now. So that's the correction. It is there on Moodle. Now let's do this one. So I want one of you to do it, all of you to do it. And one of you later on, I'll ask him to present. So what we did, what we are having here, we have a different sort of G of S. So G of S is this. We have a 0 at minus 3, which is this one. This is minus 3. And we have zeros or pools at 0, minus 1, minus 2, and minus 4. And this is my root locus. And let's say that I want my point to be along this zeta. Zeta equals 0.45 along this line. So I want my S naught to be here. I want it to be there. So to have that, this angle is cosine inverse of 0.45, this angle. This is S naught. And now I need to make sure that the angles, when I add them up, they add up to 180. So this is the angles. Phi, because this is for the 0, because this is a 0. And then theta 1, this angle. Theta 2, this angle. Theta 3 is this angle. And theta 4 is that angle. If we know this distance from here to here, and this distance from here to here, which we can calculate, what is this distance? Let's call it PTX. And this distance here is PTY. What is PTX? If you know gamma, and let's say this is R or X, this one is R from here to here, this length is R. So what is PTX?
بيكون دكتور tan.
No, the angle, we know it. We know gamma. Gamma is cosine inverse 0.45. فمعنى الزاوية. لكن باغي الضلع هذا كم طوله؟ PTX.
الكوساين بتكون اللي هي الR على البي تي اكس.
So R cosine gamma ولا؟ PTY.
البي تي واي بتكون الR كوساين
كوساين أو ساين؟
لا ساين gamma.
Sine. So sine gamma. So knowing gamma, I can calculate PTX if I assume R. So I need to assume R. يوم ما عملنا بالسابق في المسألة السابقة, we'll assume R and calculate PTX, PTY, وعلى أساسها بحسب theta 1, theta 2, theta 3, theta 4. So we'll do it that way. So with this diagram there, so this is my PTX and this is my PTY as we did it. We can calculate theta 1, theta 2, theta 3, theta 4, and so on. And therefore, we can calculate the angle and change R till we get the right R. I want you to do that now. Sorry, I'll go back here. Okay, so I want you to do that using the C lab. So you'll have 5 minutes to try it. Yeah, you need to calculate theta 1, theta 2, theta 3, theta 4. إذا تعرف gamma وgamma معروفة cosine inverse 0.45. وتحسب على اساسها بي تي اكس وبي تي واي، ومن ثم تحسب لي الثيتا 1 والثيتا 2 والفاي. So can you do it? Can you write the program? And then one of you will explain it to me. فمعاكم سي لاب ولا لا؟ You have the C lab on your laptop. أشوف ما حدا يرد. Do you have the C lab?
Yes, دكتور موجود.
Yeah, so I want you to sort of do this. Calculate theta 1, theta 2, theta 3, theta 4, and phi, and then add them up to check whether it is 180 ولا لا. If it is not 180, change R. So you'll be keeping changing R till you get the right angle. Sorry, the right what you call angle, which is 180. فبتحسبوا الثيتا 1 والثيتا 2 باستخدام A tan. يعني البرنامج بيبدأ في البداية إنك تكتب إن جاما equals A cosine degree زيتا، والزيتا معناها ب 0.45. فبتحسب هذه، بتحسب جاما، وبعد ذلك بتحسب PTX equals معك المعادلة بعد ما تحط R equals let's say 1 في البداية، and then PTY equals, and then you calculate theta 1, theta 2, theta 3, theta 4, and phi. And then you calculate the angle, which will be phi, then this is the 0, so the angle is positive, minus theta 1, minus theta 2, minus theta 3, minus theta 4, and you check, is it 180? What is the value? And you keep on changing R, you change R, till you get this angle equals 180. So I will give you 5 minutes to do it. The structure of the program, you have it. So this will be R times cosine in degree gamma, and so on. And you write the rest. So this is the program that you have to write. This is the program. So I'll give you 5 minutes. Now it is 11:42. So till let's say around 47. Sorry, this is 37. So till 47 or less than that. Then one of you will present. فبسأل واحد منكم إنه يعمل لنا presentation. If you have questions, let me know. هذه أسهل من المسألة السابقة، صح فيها ثيتاز أكثر، angles أكثر، لكن وش يسمى لأن البولز والزيروز are on the real axis, the calculation is easier. Just remember that this point is 1, yeah? This is 1, this is 2, this is 3, and this is 4. So still have another 2 minutes, inshallah. And one of you will be presenting. I'll ask one of you to present. So you can take an image or at least write it down, sketch it, so that when we discuss it later, it will be easier. So Mazen, if you can present to us, inshallah. Mazen. I will stop sharing, and Mazen will you'll start presenting. So Mazen again, if you can do it. Mazen, you can hear me? Sabahi. There is a message, so maybe Mazen is sending something. Mazen, are you there? المعتصم العدوي. إذا كنت فاتح البرنامج C Lab.
Yes, doctor. Okay.
So if you can open and share it with us, and then we can guide you, so no problem. وعسى تكون معرف الزوايا بنفس التعريف اللي كان في الصورة. If you can just make it bigger so that we can see it, لأن حاليا ما نشوفه زين. بتضطر أيضا تكبر شوية أيوة أحسن مناسب. Just move it to the side a bit إذا أمكن المعتصم، لأن كان في مربع كذا يظهر، ما أدري كان معي فقط، بحيث إن لو تنقل الويندو كلها شوية كذا لليمين. Yes, now better. Just make it bigger. Is it a bit slow? Yes. R equals 1, gamma equals A cosine. كان cosine in degree لو تضيف الword degree. Gamma A cosine degree, D. Just after S, add D. The same up there. أيوة. هذا على أساس إن الأنجل يكون in degree. أعتقد because 0.45. Yeah, it's okay. Fine. So everything is fine. So theta 1 is A tan inverse PTY over 4 minus PTX, صح؟ theta 2 إذا تعمل copy paste وتغير فقط البول والزيرو بهالطريقة، صح؟ PTY over 3 minus PTX، صح؟ بالنسبة لا هذه بتكون theta 2، هذه فاي، اللي 3 minus هذه فاي على حسب التعريف اللي معي. حسب الأرقام اللي معي، أيوة، لأن الزيرو يزيد 3. ثيتا 2 بتكون 2، صح؟ وثيتا 3 would be 1، صح؟ وثيتا 4 بيكون فيها 180 بالفعل، 180 minus 63 لأنك حسبتها already جاما، ولا كيف؟ حسبت جاما على أساس إنها 63؟
لا دكتور، من السلايد هذا؟
لا قصدي ال 63 حسبتها على أساس هذه جاما.
أتوقع الجامعة هي من السلايد جايبنها.
أوكي، أنا أتوقع هذه جاما اللي هي
أي.
63، لكن تقدر تكتبها أنت جاما لو ترجع هناك.
إن شاء الله.
إذا لديك 63 بدل 63 اكتب جاما لأنك أنت حاسبنها جاما. أيوه. الحين الانجل بتكون phi minus theta 1 minus theta 2 minus theta 3 minus theta 4. او انت بتكتبها هناك بلس داخل، اوكي نوب مناسب ايضا. theta 2 plus theta 3 plus theta 4. تمام مناسب. So now you'll just change it. You'll change R. So we'll put a table. I'll be writing here. So R equals 1. And if you run it, you get it as minus 199. Okay. And then change it to 2. And run it again. So it is minus 251. Minus 251. كأنها تزيد. إذا نقص. إلى 0.5 minus 158 ولا؟
Yes.
0.4. اوكي فمعناها بتزيد شويه على اساس تقترب من 180. اذا بتحطها 0.6 167 you'll keep on increasing. .176 this is 0.8 0.7 176 بعدين 0.8 minus 184. إذا هي بتكون between 0.7 و 0.8 فبتحطها 0.75.
180.
180. إذا 0.75 R equals 0.75. That will be the right position. أحسنت المعتصم. So I'll start sharing. So Al-Mu'tasim wrote a program similar to this one here. And I put here 63 still, but that's gamma, so no problem. I don't think I have the solution. So I'll post it later. So this is okay if you want to, let's say, choose your S naught to be along the root locus. Like let's say that I want my S naught to be here at this point. So at this point is not on the root locus. So I cannot just changing K. I cannot just do it by changing K. I need to do something else to be able to pass by that point. So root locus has a major limitation. So pools on the root locus only for different values of K are possible. But if I want to not be on A, I don't want to be here. I want to be here, which is not on the root locus. The root locus doesn't pass through that. So I have two choices. Either I modify the system, which means I modify the mechanical design, the electrical design of the system, which is expensive. Or I add a controller. So I add extra pools and extra zeros to the open loop transfer function to make it pass through that point. So that's what we will do. Now there are two ways of doing it. If you try only to do it using K, you will not be able to do it because K, you will not be able to satisfy all the requirements. So you may need to add something else. Either you do it this way, you add the compensator here. This is the compensator G1 of S. And if you add it as an integrator, you'll be able to satisfy the steady state error. So the error can be improved in this way by adding a pole at the origin. You'll make the error smaller. If you want to change the transient response to make it faster, you add some sort of a differentiator. Here you add an integrator to improve steady state error. And you add a differentiator because it makes your system faster to improve your transient response. So we can add it. We can do it by adding either a pole or a zero. So there are two ways or two major compensators. Either it is ideal sort of compensator, which is either just a pure integrator or a pure differentiator, or it's not ideal, and we call them lag and lead, and they are approximations of pure integrators and differentiators. We'll know more later when we zoom into that. So either we use integrator, proportional plus integrator, so you have the error multiplied by a constant plus the integral of the error. So that's PI, we call it. Or PD, you have proportional to the error, or and plus proportional to the derivative of the error. Proportional plus derivative. Proportional plus integral. Or a combination of both. Or you have an approximation of these two. So these are the pure integrator, pure differentiator, and these are approximations of these two. Yani lag will lead, they are approximations of PI and PD. Now, why the PI is good for improving steady state error, we know from our previous work on steady state error that if I add a pool at the origin, here, I will improve the steady state error, but I will change my root locus. So the root locus will change by doing that. So what should I do if I don't want to change the root locus? يعني نفترض اني ما اريد اغير الروت لوكس لاني انا قاعد الحين اشتغل على الستيدي ستيت ايرا، ما اشتغل على الزيتا والاوميجا، باغي فقط الستيدي ستيت ايرا يتحسن. والستيدي ستيت ايرا will be better if you have an integrator, if you have a pool at the origin, if you have a pool here at the origin, yes, a pool at the origin. But if you put it, then your root locus will change. So if I don't want my root locus to change, what should I do? أنا شوي يمكن انتقلت من موضوع إلى موضوع. الحين I want to improve the steady state error, and it will improve the steady state error putting an integrator pool at 0. It will make your steady state error better. But if you add a pool at 0, it means your angle will change. When you add up the angles, let's say this is 180. This is already 180 without the controller, without this. This is 180. If I add this pool here at 0, this one, then the angle will change. I'll be at this point in that case maybe. But if I don't want to change this angle, what should I do? If I don't want to change this one as being the sum as being 180, if I add this, what should I do to cancel this? This is a pool. If I want to cancel the effect of this, this one here, this theta, what should I do? What should I add? Any suggestions? I will add a 0. If I add a 0 very close to this, so this is the angle of the pool. If I add the angle of the 0, because this is minus, this will be plus, then they will cancel each other. So I will add a 0 close to the pool. So I can add a 0 close to this pool. In that case, this angle, because of the 0, and this angle, they will cancel each other, these two. And I will still have this as 180 in that case. So the PI, this is a PI, proportional plus derivative, proportional plus integral controller. I'm adding this to control the steady state error. And I'm adding this to cancel the effect of the pool, so that my root locus will not change, will remain the same. It will pass by, not the same, but it will pass by the same point A. مرة أخرى. Let's say I'm interested in improving only the steady state error. Okay. Steady state error will be improved if you add a pool at the origin. For a step input, what will be the steady state error? What is Kp? If you remember, Kp is the limit of S, G of S, as S tends to 0. And the error is equals to 1 over 1 plus Kp. Okay? This is the error for a step input. تمام؟ الحين إذا أضفت أنا pool at the origin, so my new G of S will be equals to, this is my new G of S, equals to 1 over S times G of S. Okay. What is Kp in this one? The new Kp will be what? The limit of G hat times S, S tends to 0. So if this one is constant here, this is constant. Let's say, if I divide by S, what will it be? S is 0. It's a small number. So what will be the limit here of this one? Yeah, let's say this is a constant. With the R is 1 over S. Sorry, I didn't put R. R is a step input, 1 over S. Let's say that this S will go with this S, and I'll have G0, and G0 is KP. But here now I will have R 1 over S, okay? But I have already in this G hat, I have 1 over S also. So this will go, but I will still have another S, this one, down. So what will it be? قاعد وش يسمى أقسم على عدد صغير جدا. Infinity. So what will be the steady state error, new steady state error? 1 over infinity, which means this will be 0.
0.
Yeah. So by adding this pool here, by putting this one, I'm improving the error. I'm making it 0 nearly in that case. But by adding this pool, by putting this pool here, I'm adding an angle. This angle. I'm adding this angle by adding this new pool. But let's say that I'm the transient response, I don't want to change it now. I just want to improve the steady state error. يعني ما اريد اغير مكان البول. هذا المكان ما اريد اغيره. ابال الروت لوكس يمر. فبالتالي ما اريد الزياده هذه تغير لي في الروت لوكس. لان الروت لوكس ما بيمر بالبوينت A في هذه الحاله. اذا if I add this, now it will not be 180. It was 180 before. So if I add this now, it will not be 180. So what should I do? I should cancel by adding a 0, this one, very close to this. فبالتالي الزاوية هذه والزاوية هذه تقريبا متساويات. فبالتالي the angle from here and the angle from here will cancel each other. فيكون كأني ما غيرت في الروت لوكس. لكن غيرت في الsteady state error. So my steady state error is better, but without changing my root locus. If I'm interested in changing the steady state error. So the PI will improve my steady state error. Will make it better. PI, نسميه PI because it's proportional to the error, because my controller now is S over plus A over S. So if I simplify it, S will go with S. I'll have K1, and I'll have A times K as K2 over S. This one is K, S over S, plus KA over S. So this one, S will go with S. I'll call this K1, plus this one, I'll call it K2 divided by S. I'll have proportional, then now this is the error. It will be multiplied by K1, multiplied by this, because I have error times K1 plus K2 over S. For E times K1, it will be multiplied by the error plus E K2 over S. And this is integration. So PI, proportional plus integral action I will have. My action, my controller, the one that will come from here now, it will be equals to E times this. And this one is EK1, this is U. U equals EK1 plus EK2 over S, which is the integration. So it is called PI. So PI, we do it that way. We add a pool at the origin, and then we add a 0 very close to it, such that it will cancel each other. This is the PI. That point is okay, I think. The PI سهل. You need to add a pool if you are happy with the root locus. The root locus is fine, and you don't want to change the place where the root locus is passing. You want only to improve the steady state error. Put a pool at the origin and a 0 very close to it. Then they will cancel each other, and your root locus will not change. It will pass through that point. Okay. So that's how you improve the steady state error. Let's say we have this example here. Okay, K times this. This is my plant, and this is my gain. My controller only proportional control. This will be my what you call root locus for this. For this one, this is the root locus. Okay, and let's say that I want to be here, as we did before, for zeta equals 0.174. So we are here. To be with zeta equals 0.174, we are here with k equals 164. هذا اللي سويناه قبل، اللي سواه أيضا معتصم قبل قليل. جبنا النقطة هذه بتغيير الآر على حسب الزيتا اللي معي، وصلت إلى هذه النقطة. With k equals 164. So let's say I'm happy with this. This is my transient response. Time to the phase peak, settling time, percentage overshoot is okay. But my steady state error is not okay. So if I calculate the steady state error, yeah, Kp Kp is the limit. I think I made a mistake there in my previous. It is not the limit of Sg of S. It is the limit of G of S. So G0 equals 8.23, and therefore my error is 1 over 1 plus Kp equals to this, 0.108. But I want to make it 0. So if I introduce this as my new controller, so what will be my plant now? What will be the overall system? It will be what? If I put them together, Gc times G. What will it be? G, we have it. This is G. 1 over S plus 1, S plus 2, S plus 10. So Gc or G will be what? K S plus 0.1 over S times 1 over S plus 1 S plus 2 أعتقد ولا؟ إذا كان معكم السلايدز.
S plus 2, S plus 10.
S plus 10. So what is my G0 now? This is my new G. So this is my new G equals to this. So what is my new G0 to get Kp? To get Kp as we did here. I'll put S equals 0. So what will I have? K times 0.1 over 1 times 2 times 10. But I have here S. So this will be 0. I still have S here, which will be a big 0 here. So this means this will be infinity. So therefore, my steady state error will be 1 over infinity, 1 plus infinity, will be 0. So my error now will be 0 instead of 0.108. Before it was 0.108. So now I'll make it 0 if I add this controller. إذا كان هذا هو المتحكم اللي أنا أضفته. A pool at 0 and a 0 very close to it, 0.1. يعني قريب منه. فما بيغير في الزاوية. So this is my controller now. If I do it that way, let me just erase this. So you can see it. I'll just erase this one here and come back again. So I put a pool at 0, this one at 0, and a 0 at 0.1, 0.1, this. الانجل ما بيكون فيه اختلاف. الإضافة اللي أنا ضفتها كأنجلز ما بيكون فيه اختلاف. هم بيتغير الروت لوكس. بيظل يو بالأول لكن حسنت أنا من الستيدي ستيت ايرور. فهذا القصد من استخدام الكي plus a pool at the origin and a 0, which is a proportional plus integral controller. Proportional plus integral controller. You have a pool at 0 and a 0 very close to it. You will get a proportional plus integral control. You'll improve Kp and therefore you'll make the error better in that case. And this is how you implement it. You have a proportional plus integral. If you add these two, you will get this one K1 plus K2 over S. If you add them up, you will put a common denominator, and then here you'll have K1S plus K2. So you'll have a pool at 0 and a 0 at this position. You'll have S equals minus K2 over K1. So you'll have a 0 at this position and you'll have S. At a pool at 0 and a 0 very close to it. A proportional plus integral control. So you will not change the steady state, sorry, the transient response. This will not change. It will be the same nearly. What will change is the error here. This is the steady state value, exactly 1 equals. And this is the previous results for not having a controller. Tariq, is it okay?
كثير دكتور.
So إضافة البول عند الزيرو وزيرو جنبها بيكون الثيتا اللي جاية من البول والثيتا اللي جاية من الزيرو كانها نفس الشيء. فما بيأثر على الروت لوكس، بيظل كما هو. فما بيتأثر الترانزيت ريسبونس. الزيتا والسيتلينج تايم والتايم تو ذا فيرست بيك ما بيتأثر. اللي بيتأثر الستيدي ستيت ايرور فقط. فالكي is sorry, the PI is easy to implement or easy to sort of design. Because you just have to put a pool at 0 and a 0 very close to it. Like, let's say that I want to improve the transient response. I don't want to improve this now, or maybe I can do this later. I can improve this later. But let's say I want now to improve this. I want to change this one here. So to do that, you can use a differentiator to improve the transient response. And the differentiator, the problem with it that you will magnify the noise. هذا المشكلة في الديفرنشيتر. يعني نفترض أن معي signal position of something and we have some noise. If you differentiate the noise, you may sort of amplify it, make it bigger when you do differentiation. When you get x dot, you will differentiate the noise, so it will be bigger. المثال اللي احب احطه هنا، لنفترض ان معي كاميرا، اوكي، وانا قاعد احدد مثلا البوزيشن of the robot and then the xy position of the robot. Okay, if I try to differentiate to get the velocity, and I have an error, let's say my x is equals to 1 meter plus or minus 0.1. لنفترض ان معي نويز، الكاميرا هذه ما تعطيني بدقه البوزيشن، فمعي plus or minus 0.1. لما احاول اجيب الفيلوسيتي of this one, the velocity x dot, what will it be? It will be 1. I mean the change in position, let's say, from the change in position delta x over delta t. لنفترض ان الروبوت ما تحرك، لكن اللي قاعد يتغير هو الايرا هذه، مرات يكون 0.1، مرات minus 0.1، مرات 0.2، مرات 0.3، يتغير الدلتا اكس، فيعطيني different value of x because of the error, because of the noise, sorry, not because of the position. The position is it didn't change, but you have some noise here. So if you put 0.1 and then let's say you put your delta t is 0.1, every 0.1 second you are measuring the position. What will be the velocity x dot? 0.1 over 0.1 will be what? 0.1 over 1. فرغم ان الروبوت ما تحرك، هذا الروبوت ما تحرك، لكن اللي قاعد يتغير النويز، معك نويز هنا في البوزيشن، مرات يقول لك 0.1 0 minus 0.1 1 minus 0.1 and so on. فاذا جيت تحسب الفيلوسيتي تعمل differentiation, you will get that the velocity is 1 meter per second رغم ان الروبوت ما تحرك. This is only the noise being amplified. So that's the problem with differentiation. You will have that problem, but it's good to use it because we need to use it to make our transient response better. Because if you know some information about the error and how it is changing, then this will make things better for you in terms of the response. So the differentiation will make my response to the error better. لأني بكون قادر أتوقع الإيرور هل هو قاعد يزيد ولا قاعد ينقص. لكن المشكلة اللي بتجيني بسبب الديفرنشيشن إن I'm amplifying the noise. I'm making the noise more by doing this. So what is proportional plus derivative? الأولاني كان proportional plus integral. Now it is a derivative, then you're multiplying by s, and then you are multiplying by a constant. يعني you're multiplying by constant, and then you are differentiating. So your error will be multiplied by kzc plus ks. This will be k1 times e, the error, plus, because of s, you'll be integrating. You'll take the error into consideration and the error dot, the rate of change of the error. So that's why we call this proportional plus derivative. Proportional because of this, derivative because you are taking the derivative of the error. And because you are doing this, you'll be faster because you'll be knowing whether the error is increasing or decreasing. So how to do it? Let's say I want to change my root locus. This is my root locus now. But now I want to change it because this will increase my, let's say, settling time or my time to the first pick. I don't want to be here. I want to be somewhere here. So I want to increase this distance. So if I increase this distance, what is my settling time? Settling time is 4 over zeta omega n. So if I increase this, my settling time will be less. I can make it less. This is the zeta omega n now. Okay. If I do it this way and put it here, my what you call root locus passes through that point, then my zeta omega n will increase. This one will increase, and therefore this will decrease, will be down. So how to do it? You put a 0 somewhere, and this will change the root locus. So I put a 0 here. Let's say I put it at -2. This is the original plant. I have -1 pool, -2, -5. This is what I have now. Let's say I put a 0 at -2. Then my root locus will be something like this in that case, and it will pass through that point. So here, if I put it at -3 instead of -2, I will get it this way. The root locus will change. It will be like this. If I put it at -4, the 0, then my root locus again will pass through the point. So I'll be able to make these changes in that way by changing the position of my 0, -2, -3, -4. And this is what I will get. I'll improve my settling time from being 4.26 second to 1.33, 1.64, 2.14, depending on where I put my 0. So I can improve my steady state, not the steady state error, I mean the settling time. I can improve the settling time and the time to the first pick. I can improve the transient response by adding a 0. Okay, and here you can see the response. This is the plant which is uncompensated. And then if I put it at -2, I will get it as such. If I put it at -3, I will get, sorry, this is -2, this one here, the blue one, this one. And this is the -3, and this is the -4. So I can improve my, what you call my transient response. But how to do it? By hand, let's say. Let's say this is my plant. Okay, there I was just trying. I was just putting it at -2, -3, -4, and I see what happens. But let's now design it. Let's say I want to be here. Okay, I want to be there. So what is the angles that I will have? This is θ1 from this pool, which is the 0. This is θ1, which I didn't change. So this is θ1. From -4, it is this angle. So this is θ2. And then from -6, it will be this angle. So this is θ3. Okay. And let's say I'll put now, and this is sorry, we have -6, -4, and 0. Yeah, -6, -4, and 0. So we are okay. Let's say I'll put my 0 here. So this will be my θz. So now I want θ1, -θ1, -θ2, -θ3, plus θz to be equals to 180. So I will get from this one θz, the angle. I can get it because I know this one, and I know this one, and I know this one. I can get θz. Now, what is θz? What is this θz? How can I get it? Tan inverse what? المسافة هذه 6.93 from here to here. So what will it be? θz? Anyone? طارق؟ شوية سريع أنا اليوم أشوفني كأني شوية قاعد أتحرك بسرعة.
It's tan inverse.
Yeah. 6.193 divided by هذه النقطة هنا زد، خلينا نسميها النقطة من هنا لين هنا. هذه زد.
Z minus 4.
Z minus
4.
Is it 4 or this value?
3.630.
So minus 3.613. فأجيب الزاوية أنا جبتها مني، حسبت الزاوية من هذه المعادلة. So it means that tan theta z equals to 6.193 divided by z minus 3.613. So I can get z from this. I can calculate z. I can know the position of the 0 to be at this point, here. طارق لو كذي مجرد for me to understand your understanding, can you summarize the difference between PI and PD after what we did بشكل سريع كذي مجرد في جملة؟ وش الفرق بينهم؟ البي اي على اساس الستيدي ستيت ايرور، احسن الستيدي ستيت ايرور بدون ما اغير الروت لوكس. والبي دي اغير الروت لوكس، بضيف زيرو فقط بالنسبه للبروبورشن بلس ديريفيتيف، وبغير في الروت لوكس، بخلي الروت لوكس يمر بنقطه اخرى. لكن البي اي لا. فوش الفارق بينهم؟ كيف اسويها؟ يعني كيف اسوي البي اي وكيف اسوي البي دي؟ هي مجرد في شرح بسيط. طارق او وحيد الرواحي، عشان طارق كرد على السؤال السابق. وحيد باختصار كذا، وش الفارق بينهم؟ وحيد. المعتصم، الفارق بين البي اي والبي دي. If you can, all of you, anyone, الفارق بين البي اي والبي دي. I'll add a new slide here. I'll just put, or maybe instead of doing it here, let me do it in this one. This is PI, and this is PD. وش الفروق بينهم؟
In PD we add zeros.
In PD we add a zero. So the PD, if I write it down, the controller will be equals something like this: K S plus Z. فبالتالي بيكون معي K times S plus K times Z. هذا عبارة عن عدد اللي هو البروبورشنال، وهذا بيكون فيها integration, sorry, differentiation اللي هو derivative. ف you put your controller GC and you have the error coming in, and the output is your control signal that will go to the plant, will go to the pendulum, will go to the tank. So my U equals to error times GC, and this is my GC, this one. So it is the derivative of the error times, this is just a number, K is a number, Z is a number, this is proportional to the error. So بيكون U equals to D times the error, so this is derivative of the error, plus P times the error. So this is just the proportional to the error. Okay. Now what about the PI? What will be my GC? You'll have what to improve the steady state error?
K S plus Z over S.
So you'll have S, you'll have a pool at the zero, and you'll have another number here.
Zero, right?
You can have it as KS plus A, let's say. You can have it this way. So if you simplify it, S over S will be just K plus KA over S. So this is proportional. This is integral because you are dividing by S. So you are adding a pool at the origin and a zero very close to it. So this is to improve the steady state error. This will improve the steady state error. And this one, the objective of this one, to improve transient response. Transient response. So here, because I'm improving only the steady state error, I don't want to change my what you call root locus. So if this is my root locus, let's say, I don't want to change it. So let's say I have a pool here and a pool there. I don't want to change that one. So what I will do, I will go and add a pool at the origin. So I'll put a pool here, which is this. And I'll put a zero very close to it. بحيث إن now this angle coming from this one and coming from this one, this additional angles will not change my root locus, will remain the same. But I will improve the steady state error. But for the PD controller, you have, again, let's say a pool here and a pool there, and then let's say my root locus will be something like this. I want to change it now. So I want to change it such that my point, that my root locus will pass through this point. So my root locus will be something like, by adding a zero there, so I'll add a zero somewhere here. I will add a zero. My root locus will be different. So this will go, let's say, to to there, and the other pool will pass, or the other what you call a pool will pass by through this point. So I want to change my root locus to pass through that point. So I will add this angle here, theta z, and I have already this theta 2, and I have theta 1, and I want now theta z plus theta 1 or minus theta 1, because this is from the pool, minus theta 1 minus theta 2 to be 180. So here I'm changing the root locus. Here I'm not changing the root locus. That's the difference between the two. You got it?
Yes, doctor.
So this one, when you do it this way, you don't have to worry about the root locus. يعني root locus will not change. انت كل اللي عليك ان تسويه انك تحط البول هنا وتحط زيرو جنبه، فبالتالي the new two thetas will not change your root locus. Will remain as it is. So that's the idea between the idea of behind using a PI controller and a PD controller, as I explained it just now here. For this particular example, you can have theta c minus theta 1 minus theta 2 minus theta 3 equals to 180, and from which you can get theta c. So we got theta 1, you can calculate theta 1 as minus 120.26, and you can calculate also theta 2, this angle. You can calculate it as we did for the other examples. And then you can calculate also theta 3, this angle. It is tan inverse this length, which is 6.93 divided by 6 minus 6.193, 6 minus 3.6, the position of this point. So you can get the angles very easily. So it's theta c that if you add this up, you will get 455, which is 95. So this angle here, theta z, is 95, from which I can get the position of the zero, this one, as we just did. We can calculate that position to have this angle, 95.6. So to get that angle here, since this one is 95, this is 95.6, so you can get this, what you call this angle here, and from which you can get the position of your z, of your zero. So you can get, it will be 84.4, this angle, BC, beta C. And tan beta C is 10.579. So tan beta C will be equal to this one, which is 6.193, divided by this one here is 3.613 minus Z, and we can calculate Z in that way. So you calculate Z, we got it as 3. So the new controller will be this. So I'll get it as this one. This is my controller. S plus 3.006. So that will be my controller. البي دي في شويه شغل مقارنه بالبي اي. البي اي مجرد تحط البول في الزيرو وزيرو جنبه. البي دي you have to calculate where the zero will be in order to be at a particular point, there. So that's the difference between the two. So this is the difference between the two. Next time we'll look at an approximation of a PI and a PD. So we'll add a pool and a zero in both. يعني حاليا احنا نضيف pool وزيرو بالنسبة للPI، لكن الPD أضفنا فقط zero like this one. But doing it in this way is not good numerically, so we may need to add a pool to it. Instead of just having a zero, we'll add also a pool to it. So that will be an approximation of a PD controller. So we'll not add a zero only, we'll add a zero and a pool. I wanted to try some of those controllers on this system and to do some sort of simulation, but I think doing it online will not be easy. So I will just answer your questions regarding what I did so far on these two controllers, the PI and the PD. And we'll do that simulation work next week. So any questions regarding?
Doctor, for our design, it will be BD or BI, or we will choose?
You will choose. You mean for the,
We'll
for the
choose.
pendulum?
For the project, yes.
Yeah, for the project you have to choose.
Okay.
And then I have to tell you next time how to implement this in your what you call Arduino, how to do it, how to implement. Proportional is easy. Proportional مجرد تضرب في constant. وهذا اللي سويتوه في الاكسبيرمنت من قبل. You have the error, you just multiply by a constant. But for PD and PI, it is a different, because you're integrating and you're differentiating. We need to know how to do it in Arduino. So maybe next week, if you don't mind, remind me so that we can go through that.